Good morning, students. Welcome to the online enrichment classes in physics for standard 12th. Today we shall discuss some questions pertaining to finding electric field due to different linear charge configurations. Now, by linear charge configuration we mean that a charge will be distributed uniformly over a length. You need to know one term, linear charge density, and as I have indicated its symbol, it is denoted by lambda. This lambda is defined as the charge per unit length, so dq upon dl. So charge SI unit is coulomb, and for length we can write meters. So for lambda we will have its SI unit as coulomb per meters. With this idea of lambda, today we shall be discussing only the linear charge distributions. So let us see our first question. You can see there is a uniformly charged ring of radius r having charge q distributed on its periphery. This is the axis of the ring. We wish to find electric field at this particular point, which is say at a distance x from the center. For doing this, what we will do, we will choose a small element, we will call it as dq. Its distance from the required point where we are finding the electric field. Using Pythagoras theorem, you can see this is our radius. So this becomes under root r square plus x square. This charge, if it is positive, we will assume this to be a positively charged ring. So its electric field will be directed away from it along this line. So we will denote it by dE vector. It can be resolved into two components like so. We will take this angle as theta. So this angle will also be theta. Let us write the components first. So this will be dE cos theta, and the other one will be dE sin theta. Now the value of this dE is how much? That will be 1 by 4 pi epsilon naught into this charge element dq by this distance square, that will be r square plus x square. Before finding dE cos theta, dE sin theta, if we employ the concept of symmetry, we choose one more element over here having same value dq, lying at a point diametrically opposite to the previous point. Due to this, these two are lying on the diameter, at the end points of the diameter. Due to this charge element, the electric field will be like this and will have same value dE. And symmetry says if this angle is theta, this angle will also be theta, and therefore this dE can also be resolved like so. It will have one component here, that will be dE cos theta, and one component will be like so, that will be dE sin theta. Likewise, we can choose other pairs of elements lying on the end points of the diameter. It's clear from this particular resolution of vectors that the components dE cos theta, they are in same direction, but the components dE sin theta, they will cancel because they are in opposite direction, and that gives us the hint that the net electric field will be then found by summing over all the elements this component, that is dE cos theta. So we will integrate it. If we take into consideration all the components, all the elements, then their dE sin theta, as I have discussed, will cancel. So this becomes how much? dE is 1 upon 4 pi epsilon naught dq upon r square plus x square. This is the value of dE. Then we have to put the value of cos theta. Cos theta, you can see this triangle is base, that is x, upon hypotenuse, that is under root r square plus x square. So we will integrate this one. Now you can see 1 by 4 pi epsilon naught is constant. x is constant and these two terms become r square plus x square to the power 3 by 2, that is also constant. So what is left behind is only integral dq. Now dq was the small element on this ring. If you integrate dq, that will just add the charges on all the elements, and that will give the total charge on the ring, which is nothing but capital Q. So this will become capital Q, and that gives us the value of electric field, and the direction is obvious, it is along the axis. It will be directed like so, in this direction if this ring is positively charged, and in opposite direction if this ring is negatively charged. Now it's important to see this particular interesting expression. This expression will become 0 under two conditions. First, when x is equal to 0, and then when x tends to infinity. The second part you can test it yourself using the concepts of limits which you have read in mathematics in standard 11th. X is equal to 0 is obvious, the numerator becomes 0, so electric field is 0. When x tends to infinity, we say this term in the denominator, x square to the power 3 by 2, so 2 cancels, it behaves like x cube. So x upon x cube is like 1 by x square, and that's why at x tends to infinity, the electric field again approaches to 0. If the electric field is 0 at x is equal to 0 and x is equal to infinity, that means which point is x is equal to 0? It is nothing but the center of this ring. And x is equal to infinity will be very, very far from the ring. At these 2 points, the electric field, if it is 0, then in between, since the value is non-zero, it means it must rise from 0 to some high value, becomes maximum, and then falls like so. If you are asked to plot the graph of E versus X, in this particular situation, it will be like this. It will be 0 at x is equal to 0, and again it will turn 0 at infinite separation. So it will become 0 at x is equal to infinity. And this is the point of maximum, which actually we will find that occurs at x is equal to a by root 2. On this side, actually you can plot the graph over this side also. The electric field value for negative x is also defined. It will be just a mirror image of this. So its replica we can draw. Imagine a mirror over here. So at x is equal to a by root 2 or minus a by root 2, under these two situations, the electric field becomes maximum. Now how do we prove this value? That can easily be seen from this expression for electric field. So this is our electric field. We see electric field is a function of x. This electric field, for it to be maximum, so E will be maximum if dE upon dx is equal to 0. That means d by dx of E. Now this part is constant, so we can leave that part, remaining x upon r square plus x square to the power 3 by 2. This derivative will be equal to 0. I think this need not be done by me. It is a simple mathematical problem. In 2 steps, just you find the derivative, equate it to be 0, and you will get the answer x is equal to plus minus a by root 2. The graph I have told you. If you are asked to find this maximum value of electric field, then how will you find that? That maximum value of electric field can be obtained from this expression only, just by substituting that value of x for which E is maximum. That is x is equal to a by root 2. So put x is equal to a upon root 2. So this becomes r square plus a upon root 2 to the power its square to the power 3 by 2. One thing I have committed, I would like to change. This a actually should have been replaced by r. The radius is r actually, so instead of a it should be r. So this will be r by root 2. Everywhere I should write r. R is the radius, A is not the radius. So this will be R. This can further be simplified, which I am not doing, and that expression, final expression, I suggest you to solve it yourself, will give you the final maximum value of electric field due to a ring of charge. So this was our first question. I suggest all of you seeing this video to take a pause, solve this question yourself in your notebook. If you find some problem, see the video and then proceed further. So let's see the next charge distribution and find its electric field. This is our second question. Here you can see there is an infinite line of charge. There is a very long line. On that line, charge is uniformly distributed and the charge per unit length is lambda. Due to this infinite line of charge, it does not have the end, it does not have the beginning. We have to find its electric field at some distance, say r, from the line of charge. This point is some point, say P. At this particular point, we have to find the electric field. So we choose this point where this line, from this point we drop a perpendicular. This point we choose as x equals 0. At a distance x, we choose an element. For the sake of clarity, I have drawn this element so very thick, but remember it will be very, very thin. At a distance x from this point, we'll choose an element whose thickness will be dx. And it will have some charge, say dq. Charge on it, we'll take it as dq. Now since lambda is the charge per unit length, you can write, students, that the charge on this particular element will be lambda times dl. Because lambda is charge per unit length, charge will be lambda into length. So lambda into this length is dl. So that is the total charge on that particular element. Now we will find its electric field at this point. Its electric field will be dE vector. It will be in this direction. This can be resolved into two components like in previous case. So we will choose this angle as theta. So this will be dE cos theta and this will be dE sin theta. Now we'll integrate them separately. Symmetry says if it is infinitely long, then this component, if you choose an element over here, then it will have two components, this and this. So these two components will cancel. But we'll generalize this particular case by not taking infinite line of charge, but by taking a finite line of charge. Then symmetry will not hold true. We can have more length here, less length here, or less length here, more length here. In that case, we have to find both these components of electric field by integrating. So let us first discuss the finite line of charge. So it has a finite length from here to here, and then we will switch over to infinite case. So this electric field has two components. One of the component is perpendicular to the wire, that I will call as E perpendicular or dE perpendicular, and that is how much? dE cos theta. And the other component is parallel to the length of the wire, so that is dE parallel, and that is how much? dE sin theta. Let us see how to do this calculation. So due to all the elements, if we wish to find the electric field, then let us first simplify this. Then we have to integrate this one. That we will do later. Now see, dE. dE is this value of electric field at this point due to this element. That will be 1 by 4 pi epsilon naught. This charge is nothing but dq upon this distance square. Now this is x, this is r, so this is x square plus r square under root. But we have to take its square, so it becomes x square plus r square. And then cos theta. Cos theta value will be how much? You can see in this triangle, cos theta is base, that is, that will take it up, wait, I'll simply write cos theta. Here the variable that we have chosen is x. We wish to convert this dq in terms of dx. Now as I have written here, dq is how much? Lambda into length. Instead of dl I should write lambda into dx, because the length of this element is dx. So dq I will substitute by lambda into dx. Now what's the relation between x and r over here? You can see in this figure that tan theta is x upon r. This implies our x is r tan theta. We need dx. So derivative of x should be r. Derivative of tan theta is sec square theta and then d theta. Please convince yourself that these equations are okay for you. So I'll put dx value over here. So this becomes 1 upon 4 pi epsilon naught lambda. Dx I'll write as r sec square theta d theta, then this term cos theta, and then divided by x square plus r square. Now what is our x? Our x is r tan theta. So this becomes r square tan square theta plus r square. So we can take r square common in the denominator. If you take r square common, you will be left with tan square theta plus 1. You know that 1 plus tan square theta is nothing but sec square theta. So that sec square theta will cancel with this. So what is our final expression then for this? It becomes 1 upon 4 pi epsilon naught lambda r and r square, one of them will cancel, d theta and cos theta. This is our DE perpendicular. So cos theta d theta, let me write this way. Therefore the total electric field along this direction due to all the components, how will we find that? We will find that by integrating this term, and that we will denote by E perpendicular. So this will be simply integration of this. Now when we integrate this, you can see 1 by 4 pi epsilon naught. So this becomes 1 by 4 pi epsilon naught lambda and r, all of them are constants. What is left behind is cos theta d theta. Now the next thing that is important, you have to understand what is d theta in this figure. This is the direction of increasing theta. If I draw a line like this theta is small, now theta is more. As I go like so, my theta will increase. So this is theta, and if I draw the line from the other end of the element, this angle will be theta plus d theta, so that this small angle is d theta, this one. So theta is increasing in this fashion. Now I have to take the element from one end of the wire to the other end. So let me represent that by a line like this. Let this angle be alpha and this angle be beta. Then can you think about the limits of the integral in this case? How should I choose the limits for theta so that my entire line is covered? So theta will change like this. This is theta is equal to 0. Theta will start from this part, it will become 0, and then it will start increasing. So theta is increasing in that direction, so this is the direction of positive theta. The first you have to move opposite to that direction, that means in the direction of decreasing theta. So this direction we will take as negative. That is very important point. So this angle alpha, we should write it as minus alpha. Let me repeat again. This is the direction of increasing theta. Theta is increasing in that direction. Since we are moving opposite way in the direction of decreasing theta, we will take this angle while putting the limits as negative. So from minus alpha, the angle increases, it becomes 0 at this particular location. So this is minus alpha by 2, minus alpha by 4, then it becomes 0, then it becomes positive something, then beta by 2, then it becomes beta. So the final limit will be beta. Now that can be further simplified. So this becomes how much, students? What is integration of cos theta? Integration of cos theta is nothing but sin theta. So I will write here sin theta, and the limits will be from minus alpha to beta. So this becomes 1 upon 4 pi epsilon naught lambda then r sin beta minus sine of minus alpha. But sine of minus alpha is minus sine alpha, so it will become plus. So that is our final expression for electric field in this direction, that is E perpendicular. Please remember this particular expression. So I am writing here, commit to memory. Let us see what happens to the other component. The other component DE parallel was DE sin theta. In the same fashion you will proceed. Put the value of DE, we will get this much, but instead of cos theta there will be a term sin theta. So E parallel likewise will be integration of DE parallel. In same fashion we will proceed. All the things will be same. Instead of cos theta there will be sin theta. So this will be 1 by 4 pi epsilon naught lambda sin theta d theta by r. And what will be the limits of integration in this case? Same, that is from minus alpha to plus beta. Now what is integration of sin theta? Integration of sin theta will become minus cos theta. Other parts will be constant. So integration of sin theta d theta will be minus cos theta. The limits will be from where to where? Minus alpha to beta. So rest part, see 1 by 4 pi epsilon naught, I am writing it as k, just to remove my work, to reduce my work. So 1 by 4 pi epsilon naught I will write as k. So this 1 by 4 pi epsilon naught I will write as k, lambda and r, so lambda by r. Now just put the values. So k lambda by r minus cos beta minus cos, so minus minus will become plus, and cos of minus alpha, but cos of minus alpha is same as cos of alpha. I would suggest you to do this yourself. So this is our expression for the electric field parallel to this particular. So please memorize these two relations. Let me summarize them one by one. We have got two components of electric field. The total electric field perpendicular to the line of charge, that we will write as E perpendicular in that particular direction, and that is how much? K lambda by r times sin alpha plus sin beta. One word of caution here, while calculating the integration we have taken the limits from minus alpha to plus beta, but for calculations, if suppose this is 45 degree and this is 60 degree, don't put alpha is equal to minus 45 degree. Already that sign has been taken while doing the derivation. So next time when you get some numerical problem, put alpha is equal to 45 degree and beta is equal to 60 degree. Already the sign convention has been taken into consideration. And the other component of electric field, that is in this particular direction, E parallel will be how much? K lambda by r times, you can see there, cos alpha minus cos beta. Now if cos alpha is greater than cos beta, this term will be positive, this direction will be correct. But if cos alpha becomes less, then this term will become negative and then the field will be in that particular direction. You know, students, cos alpha will be greater than cos beta if alpha is smaller than beta. If alpha is smaller, for small angles cos value is large. For example, cos 0 is 1 but cos 90 is 0. If alpha is less than beta and both of them are acute, then cos alpha will be greater than cos beta. Then electric field parallel component will be in this particular direction. But if alpha is less than beta, then cos alpha will be less than alpha is greater than beta, cos alpha will be less than cos beta. Now what is the purpose of discussing this? If you have a situation like so please memorize these two relations. If you have a wire which is charged like this and you are asked to find electric field at that particular direction, one component will be like this and the other component, now you can see, students, if you drop the lines to denote angles alpha and beta, here you can see alpha is less, so cos alpha will be more. That clearly indicates the electric field parallel component will be in this direction. But if you have a situation like this and you have to find electric field direction over here or value over here, so this will be your E perpendicular. E perpendicular, there is no doubt, always away from the wire if it is positively charged and towards the wire if it is negatively charged. And now this angle is smaller, so this time here the E parallel component will be like this. At the midpoint of the wire, these two components will cancel. So always remember, if we have a finite length of the wire, this is the midpoint. At midpoint, this component of electric field will be 0. For other points below the midpoint, the electric field will have components like this. And above the midpoint, the electric field will have components like this. Always remember this particular discussion. So this was a interesting question and there will be number of problems based on this particular derivation. Let us briefly discuss what happens if we have infinite line of charge. You can see here, students, so this was finite part, this was alpha, this was beta, this is distance r, lambda was linear charge density. Now if this wire extends to infinite on either sides, then this alpha we have to increase its value. Can you guess what are the limits alpha and beta in this particular case? You can see this line will become, this angle alpha will go on increasing like this, and when this becomes infinity, this line will become almost parallel to this particular wire. So alpha will become this much, that is pi by 2. So alpha becomes pi by 2. Just now I explained, you don't put alpha is equal to minus pi by 2. Alpha is equal to pi by 2. Already that sign convention has been taken into consideration. And then beta is also likewise. You can see how beta will increase and increase and increase, and ultimately will become parallel to the wire, this line, and in that case beta will also become pi by 2. Putting these two values, you can see E perpendicular will become how much? Sin pi by 2 plus sin pi by 2. Sin pi by 2 is 1, 1 plus 1, 2, so it becomes 2k lambda upon r. And E parallel component will become cos pi by 2 minus cos pi by 2. Cos 90 is 0. Cos 90 is 0. So this becomes 0. So always remember, if we have infinite line of charge, then at some point distant r from it, the electric field will be in this particular direction or in this direction depending upon the sign of charge, and its value will be how much? 2k lambda by r, where k is how much? 1 upon 4 pi epsilon naught. There is no component of electric field in this particular direction. So this is for infinite line of charge. There is yet another case of semi-infinite line of charge. Let's see that. You can see the figure over here. So this is our infinitely long wire, but the point where you have to find the electric field is near the end, is at this end. You can think of this situation. This is an infinitely long wire, but you are present at its end. You know it's one of the ends, but other end is at infinite separation, and from you at a distance r, you have to find the electric field. So we know there are two components, electric field E perpendicular, E parallel. Now what are the two values of the angles which we have taken into consideration? See, this is to be our alpha, but in this particular case, the alpha is 0. So we set alpha is equal to 0 in this situation, and beta you can see beta, as per previous discussion, the line will become parallel to this, so beta will tend to pi by 2. The alpha, if it is 0, then in this expression if we put our E perpendicular will become how much? K lambda upon r sine pi by 2, sorry, sine 0 plus sine beta is pi by 2. Now sine 0 is 0 and sine 90 is 1, so 0 plus 1 will become 1, so our answer will be this one. In case of infinitely long charge, infinite line of charge, this component was 0. But let's see what happens here. E parallel will become how much? It will be k lambda upon r cos alpha minus cos beta. Now what is alpha? Alpha is 0. So this becomes cos 0 minus cos beta. What is cos beta? It is pi by 2. Now what is cos 0? 1. And what is cos pi by 2? It is 0. So this will vanish. So how much will be left? 1 minus 0, that is nothing but 1. So it's interesting to note that both these components have same value k lambda by r and k lambda by r. So if we are asked to find the net electric field, you can simply use the parallelogram law, and you can see that the diagonal, that is E, gives the net electric field, and both of them are same, therefore this will be a square, and this will be under root E perpendicular square plus E parallel square. On solving you will get k lambda by r root 2. Root under this square plus this square, so you can solve it out. You will get root 2 k lambda by r, and this angle is clearly how much? 45 degree. Because these two sides are equal, tan 45 must be this by this, that is 1. So we know tan 45 degree is equal to 1. So what we have discussed, let me summarize, students. We have discussed the method for finding electric field due to a finite line of charge. Then we have seen infinite line of charge, and then we have seen semi-finite line of charge. This situation we call it as semi-finite line of charge. So there will be many numericals based on these particular situations. So please practice them, learn the derivation, and also you have to by heart the obtained formulae. One more case I shall discuss today. This pertains to finding electric field due to an arc. Arc, you know, students, it is a part of circle. So I can remove this part of a complete circle, then this becomes an arc. And this arc subtends at the center some angle, that angle I have chosen as phi. What would be the electric field at this particular point? See, symmetry says, if you see the symmetrical nature of this particular arc, the net electric field must be in this particular direction. But we will try to prove it. So as usual, we will choose an element of length dl. Lambda is the charge per unit length. So on this element, the charge dq will be lambda times dl. So due to this element, the electric field, this is the reference. So angle I will start measuring, angle I will measure with this as the reference line, this way, this way. So this angle is suppose alpha, then this angle is also alpha, then this is the direction of increasing alpha. So if I draw this, then this angle will be d alpha, alpha and d alpha. the element subtends an angle d alpha at the center. So quickly see, this is the electric field direction due to this element if it is positively charged. So I will write it as dE. There will be two components. One component will be like this, one component will be like this. This will be dE cos alpha and this will be dE sin alpha. If you choose one more element over here, symmetrically lying at the opposite end of this reference line, then its electric field will be like so. It will have two components, one here, one here. So you can easily see that these two components will cancel. Therefore, the net electric field will be in this particular direction, and that net electric field value will be nothing but integration of dE cos alpha. Rest you can find it easily, students. dE is the value of electric field at this point. That is nothing but 1 by 4 pi epsilon naught, which I will write as K, into charge. Charge is dq, but dq will be lambda times dl by distance square. This distance is the radius, so r square. So k lambda dl by r square is the value of dE. And then we'll have cos alpha. Cos alpha, how do we convert? We'll put it simply like so. So this is our integral. Our variable is angle alpha. So we want to convert dl in terms of alpha. How can we do that? You can see this angle d alpha is nothing but this length dl upon this r. Therefore dl will be how much? R times d alpha. So electric field E will become K lambda, dl will put as r times d alpha, and this is r square, and then we have cos alpha. So one r will cancel. We have to integrate this. Again, what will be the limit? Alpha we have to take from this part to this part of the ring. Now this is the direction of increasing alpha. This is alpha is equal to 0, this line. So first we are moving in the direction of decreasing alpha. So this angle must be negative. Now what is this angle? This is half of this total angle. This total angle is phi. So this is phi by 2. So I must write here phi by 2, but with a negative sign, because we are moving in the direction of decreasing alpha. From minus phi by 2, alpha will increase, it becomes 0, and after 0 again it starts increasing and will reach to this particular point, that is phi upon 2. You can easily solve this particular integration. So this becomes k lambda r integration of cos alpha d alpha. Now what is the integration of cos alpha? So cos alpha integration is nothing but sin alpha, and the limits will be from minus phi upon 2 to plus phi upon 2. If you put this value, so this becomes k lambda upon r sin phi by 2 minus sin of minus phi by 2. But sin minus phi by 2 is minus of sin phi by 2. So this 2 will become plus. So sin phi by 2 plus sin phi by 2 will become twice of sin phi by 2. So that is your answer. So please remember this particular relation also, that the electric field at this point, it will be in this particular direction, and its value will be how much? 2k lambda times sin phi by 2 divided by r. K lambda sin phi by 2 upon r. This k, should remember students, it is nothing but 1 upon 4 pi epsilon naught. So this was very important. This and the previous case what I have discussed together, I will put up a question which you should try at your home. See, first a simple one. Here there is an arc. This is nothing but a quadrant of a circle, and it has charge q, some charge distributed over it uniformly. Lambda is the linear charge density, its radius is r. You have to find electric field at this particular point. So this is an arc of a circle, and just now we have discussed, students, how to find electric field due to an arc of a circle. If you see, this arc subtends how much angle at the center? 90 degree. So here in this formula we will put phi is equal to 90 degree, and we have seen that the electric field over here will be in this particular direction, symmetrically lying on that particular arc. So it will make how much angle? 45 degree. So this is our E vector. So what will be the value of E? It will be 2k lambda sine how much? 90 by 2, that is 45 degree by r. Now sine 45 becomes 1 by root 2. So this will become root 2. This root 2 and this 2, you can put it like root 2. So this is the net value of electric field at this particular point. If we wish to write in terms of vector, then you can see this E vector can be written as Ex I cap plus Ey j cap. Now Ex will be how much? Ex will be root 2k lambda by r, that is the value of E, times cos 45 and then I cap plus how much will be Ey? Root 2k lambda by r times sine 45 and the unit vector will be j cap. Now cos 45 will be how much? 1 by root 2, that root 2 will cancel with this. Likewise sine 45 is 1 by root 2, that will cancel with this. So this is your answer for the net value of electric field. You can see these two values are same, and that's why it will lie symmetrically about these two perpendicular axes. Please try this question as homework. This is semi-infinite line of charge, and then it takes a turn like an arc. This arc is like this quadrant, and then again extends till infinity. This arc is of some radius, say r. At this point, you have to find the net electric field. So E is equal to question mark at this particular point, and it is given that the entire charge distribution is uniform and lambda is uniform linear charge density. Let me give you the hint. Here you will divide it into three parts. This is part 1, which is infinite line of charge, semi-infinite in fact. You are standing at the end of it. Then from here to here, that is part 2, and this is just now we solved how to find that, E3. So the net electric field will be E1 plus E2 plus E3, and you have to add them using vectors. I will stop here, students. I earnestly request you to please practice all the derivations which I have discussed today and try to solve some numericals on your own. And I will put some of the assignments. Please try them sincerely. We will discuss most of them in our next class. Thank you. See you in the next class.